Welcome back, and what you have just seen was a concrete cylinder compression test in action. Okay, it is commonly known as a CTM, which stands for Compressive Testing Machine. So look, in this presentation, we will talk about the concrete stress-strain curve and its relationship with the concrete properties. Okay, the stress-strain curve is the graphical results that derived from the CTM that you just saw. So on this general diagram here, the vertical axis represents the compressive stress or strength, okay, of the concrete, while the horizontal axis represents the strain, which is the deformation experienced under the applied loads. Now, this applied load from the CTM is typically controlled and increased gradually. Now, the resulting stress-strain curve is kind of unique for each concrete mix, and it varies based on the compressive strength F-C. So you can see here we have different sort of curves for different strength. Now let's look at an example of this particular curve here. Let's take this curve here. At the peak of the curve, the concrete reached its maximum compressive strength F-C, which in this case it's 25 MPa. Now the corresponding strain at this peak is known as epsilon sub c, and it's approximately 0.0022. I think it ranges between 0.0022 till about 0.0025. We can call it 0.22%. Now beyond this point, the material begins to fail, and the ultimate strain, which is at the end, it denotes as epsilon sub cu, which is about 0.003. Okay, and that's 0.3%. And that is specified in AS 3600 2018. This is generally called the usable maximum strain, or the rupture strain, if you like, at a point where the concrete completely collapses. Another important feature of this curve is the initial slope, which remains linear up to around about 45% of that peak stress of F-C. Now, this linear portion represents the modulus of elasticity, and sometimes we call it the secant modulus, okay, E sub C. All right, that's just a quick introduction of the stress-strain curve. Let's dive into it and unpack this slowly. Okay, there are three main questions we might need to ask ourselves. Number one, what is the definition of stress and strain? Okay. Also remember, concrete is a non-ductile material, unlike steel. Now with steel, we can look at the engineering terms of stress and strain versus the true stress and strain. Okay, they're two different things. Now, engineering values are the ones that we use in our design. Okay, they're basically within the linear elastic regions. Okay, whereas true stress and strain are instantaneous values, which depends on the change of the cross-sectional area with the change of loading. Okay, and I think, look, we can speak about true stress and strain in another video. The second question is, why is this curve so important when designing concrete elements? And the third question is, what are the phases involved in the concrete stress-strain curve? What are the phases that we need to be aware of when designing the concrete elements? Okay, number one, what are the definitions of stress and strain? Okay, what is stress? Now, for non-ductile material with small plastic deformation, we often use the term nominal stress, or sometimes called the engineering stress. Okay, nominal stress is simply defined as force divided by the original area. Okay, in this compressive or compression testing machine, like this photo that we have down here, the force is applied onto a cylinder or a cube, a concrete cube, until concrete failure occurs. Now, generally, a cylinder test is more conservative than a cube test. In the case of a cube test, the original area is simply the length times the width, okay, L times W, and the cylinder test is the area which is pi d squared over 4, or pi r squared. In Australia here, we use a cylinder that is about 100 millimeters in diameter and about 200 millimeter high. I think that's the sample that we use in Australia here. Pretty sure that this is the standard size. The units for stress is force per unit area. So, it could be MPa, which is commonly used, Newton millimeter squared, or kPa or Pascal. Yeah, so let's, now with this concrete in uniaxial tensile test, which is, uniaxial means the test is in one direction, okay? So you're pulling the cylinder out in one direction outward. That's the uniaxial tensile test. We will get a very small tensile strength, okay? So if you take that cylinder and try to pull it together, pull it apart, it will give you a very small tensile strength, and it would crack almost straight away. Now this uniaxial tensile strength is determined to be approximately 0.36 square root F-C, okay? And I think this is in clause 3.1.1.3. Okay, that's in AS 3600 2018. I'm sure around the world you'll have a different value for that. So please check your code. Now, there is also a flexural tensile stress or strength. So when you get the beam and you bend it and it's under flexural, it will crack at the bottom in tension. This is what we call a tensile due to flexural. Tensile stress due to flexural, which is about 0.6 square root F-C. Okay. Now this is a like I said, it's shown mainly for a test where we have a simply supported beam and it's under pure bending. As we note here that the flexural tensile strength is approximately 67% greater than the direct or uniaxial tensile strength. Okay, now for this reason, concrete would behave better as a beam or a slab element rather than, for example, a stump. Let's assume a concrete stump that's taking direct uplift forces, or concrete columns, or a pier subjected to a high uniaxial tensile forces. It's a better element that takes flexural forces, or flexural compression and tension, which causes bending. Okay, what is strain? The strain is simply the change in length due to the applied load, whether in tension or compression, divided by the original length L. So like we can see in this photo here. So when we record the strain limit for concrete, we are mainly concerned about the compressive strain. For steel, we would be more concerned about the tensile strain in the material. Two values we need to put in mind with this stress strain curve. On the horizontal axis, epsilon sub c, which is approximately 0.002 till about 0.0025. And this is the concrete strain at peak compressive stress, F-C. At the limit of F-C, the concrete now begins to crush, and it's important to understand this concept. Then the second strain parameter, which is epsilon sub cu, which is 0.003, 0.3%, which represents the ultimate strain, and that is the rupture. It's the rupture strain, and this is what we can use in our design. So this strain, again, the value for this strain doesn't have any units. So in this case, it could be millimeter divided by millimeters. It's unitless. Right, so the second main question that we might need to ask is, why is this curve so important when we design reinforced concrete elements? Now, I'm guessing by now you kind of figured out why this curve is important. It's all about determining, or the determination of F-C, which is the peak compressive stress, and as well as the Young's modulus, or modulus of elasticity, and then as well as the rupture strain. So we have three components here that we need to look at. Now, all of these parameters are first dependent on the concrete materials and the mix ratio. Okay, this is very important, and that's the relationship between the properties of the concrete to the stress strain curve. All right, now what is concrete made out of? What are the ingredients? Aggregate, which is a mix of rock and gravel. We can have coarse and fine aggregates, but put in mind that aggregates can sometimes carry moisture, okay, and this moisture levels can exceed the saturated surface dry condition. So we have to calculate the water content in that mix, right? From especially from the fine crushed rocks. Okay. It also has sand, and it has water and cement. All right. Now, when cement and water are sort of combined together, they form like a paste that binds the sand and the aggregates together. and this cement water mixture often referred as the binder. It's like a polymer because it holds everything, sort of holds all the components together. The water cement ratio is very important, and that impacts the concrete strength, and it should be kept to around 0.5 to 0.55. Again, this will ensure concrete workability without affecting the strength. Again, I'll show you a table later on with the relevant water cement ratios and all the other mixed ratios of aggregate cement, sand, and water. We'll go through it in the next couple of slides. Okay, now why is the proportion of this mix very important? To understand strength and behavior, which is the deformation of concrete, the concrete elements, okay? Now this proportion of mix will heavily influence the compressive strength and strain of the concrete. So depending on the mix we use, in that CTM to carry out the cylinder test to work out that peak compressive strength, F-C, then we can find out the capacity or the peak stress that we can use in our design. Now, how can all of this help us in designing, when we get to know F-C? Now, from working F-C and the modulus of elasticity, we can then work out the uniaxial and flexural tensile strength, which is F sub CT and F sub CTF, the tensile strength that we spoke about before. And that will help us to understand that first cracking strength and the tensioning, stiffening properties of the concrete. From working out F-C, we can obviously work out the compression strength of the concrete elements and the width of the compression block as well in bending. That we can figure that out from F-C. We can also work out the shear strength as well, and for serviceability, we can work out from working out modulus of elasticity. We can then work out the stiffness and the deflection and determine the deflection, the crack width, which then depends on the flexural rigidity, and sometimes we call it the bending stiffness. So we can work all of these properties out from once we determine the peak compressive stress in the concrete. All right. Here let's have a look at the table. I've got a shot here of the table that you can see the values of the compressive strength with respect to the ratio of cement, sand, and aggregate, and water, and the water cement ratio. And you can see here, as you notice, that the greater that water cement ratio, the strength grade of the concrete dramatically decreases. Yeah, so we have to make sure that we're careful with the amount of water we put in the mix. Okay, now these are just empirical, and these values here that I have are just for general guidance. So yeah, always validate this with the trial mix and the test results that you get on site. Okay, now let's look at the third point, the third question that we have. What are the phases involved in the stress-strain curve that we need to be aware of? The stress-strain curve can be divided into three main stages, okay? A, the initial linear elastic region, sometimes it's called the recovery or the recoverable stage. We start here at zero and, zero stress, zero strain. And once we apply the load from the CTM, then the load is just gradually applied. The stress strain is proportional, okay? And that line here is linear. Now the line is linear to about 30 to 40%, sometimes up to 45% of the ultimate compressive strength F-C. Young's modulus, the initial tangent modulus, if you like, applies with this line. So the slope of that linear line is the value of the initial tangent modulus, okay? In the recovery phase, the material is still elastic, which means that if we apply the load on the member will deform. But if we take that load off, then the member will recover again, and the geometry of the member will be exactly the same as how it started. Okay. So micro cracks will begin to form microscopically, but you will not be able to really see that first crack. Okay. Phase B, then we move to the non-linear ascending region. Okay, the stress continues to increase, but at a diminishing rate in a shape of a parabola. Again, microcracks propagates, modulus of elasticity, the stiffness starts reducing. You can see that here in that little curve. So flexural and axial rigidity of the material will begin to reduce. The concrete reaches peak stress at F-C at the strain of 0.002, okay, till about 0.0025. Now this peak stress this is what we use in our design. And concrete at that point begins to crush under the compressive stress. Okay, and then the final phase, phase C, is what we call the descending or post-peak region. Now, after the peak, concrete loses strength with increasing strain. Right now, at this point, once the line begins to curve, then that's it. You're in the plastic region now, which means it's not a recovery state anymore. You could never go back to the initial volume, the initial cross-sectional area of the concrete. It's now deformed, especially with concrete. You begin to, because it's so brittle, it begins to fail. Now, regions is considered highly non-linear and unstable. Strain softening occurs, and this is the rupture point has reached at the ultimate strain epsilon sub Cu, and that's 0.3%. Okay, here if you want to know the formula for the mean average modulus of elasticity throughout that curve, what mean average we use. Yeah, so if you want to know what this formula is, you can go to AS 3600, and it's in clause 3.1.2. Okay, and they use the mean average stress, F sub CMI. This is the mean compressive stress. Now you could still use F-C instead of the mean average stress, which is more conservative. I use F-C to work out the modulus of elasticity in this equation here. So you got two equations. One, if the mean compressive stress is less than or equal to 40 MPa, and the other formula if we have it greater than 40 MPa. But this formula is for normal weight concrete, which is 2,400 kilogram per meter cube, and that's the density. We consider that as normal weight concrete. So you just input 2,400 in this formula to the power of 1.5 and follow the rest of the equation. Okay, one final important observation, and we spoke about it before, one final observation from that stress strain curve I'll just touch on again. Now, as you can see here, as concrete strength increases, for instance, moving from 25 to 50 MPa, the rupture strain decreases. So for high strength concrete, you have to be careful with the rupture strain. Okay, so as F-C increases, now epsilon sub Cu decreases. And according to 3600, the maximum usable strain that we can sort of use for normal strength concrete is 0.003. And this is important because it's relevant for members subjected to flexural and axial loads. Okay, now the value may vary slightly, just depends on the country that you're in and which code you're following. I know in Canada they might be using 0.0035, while some European standards they use 0.0025. Okay, so the strain limit is fundamental when designing members like beams and columns. Okay, all right. I think this wraps it up. Wraps up the presentation. Now, if you have any questions, please feel free to ask in the comments section below. Hope you found this explanation helpful. Please share, like, and subscribe so that others may also learn. Thank you once again, and we hope that you have a great afternoon.